Hi, these are notes about molecular polarity. So if you remember, we talked about bond dipoles and sorry, it's possible that you can have, two things that are bonded, and you can have one of those elements in that bond pulling those electrons harder than the other. So then we would draw this dipole pointing towards the one with the higher electronegativity and away from the one with the lower. And then this becomes partially positive on the end that it pulls away from and partially negative on the end it pulls towards. So if you look at a molecule, though, you need to look at the whole thing. I'm not going to draw my electrons, but each of these fluorines would be pulling equally and essentially cancel out. So this would be, if I were to draw a circle around this whole molecule, it is nonpolar. I don't have an accumulation of negative on one end, positive on the other. However, if I have, maybe this, and I have a dipole and a dipole, and even if I had a dipole here, which I don't because I think it's a 0.4 difference, only draw the dipoles when it's between 0.5 and 2.0. But even if I did, they're not identical atoms to these. So there's going to be some lopsidedness, some pulling. One side's going to pull harder than the other. So if I were to draw like a circle around this end with the fluorines is going to be partially negative, and this end with the hydrogens is going to be partially positive. So you guys did the PHET, and I'm just going to move my picture out of here. It's always in the way. Okay, so which shapes are always polar? You would want to say, sorry, grabbing my pen. The shapes that are always polar are going to be bent and trig pyramidal, because those are not symmetrical shapes and because they have lone pairs on the central atom. So you can see like water it has, the PHET didn't show you this, but when you draw it, you know that there's really two lone pairs here. And that's always going to make that end more negative. So partially negative and then partially positive on this other end of water. Pyramids are the same or similar. So a pyramid, again, you can't see it with the PHET, but we know that when we draw a pyramid, there's a lone pair sitting up here. Very negative. So that end of the pyramid is always going to be negative. Other end is positive, which makes it always polar. What shapes, no, this isn't worded right, but there are some shapes where as long as everything cancels out. Okay, so which shapes are always nonpolar? If you have like a linear shape, sorry, if they're identical atoms, they're going to pull exactly the same. Those are always going to be nonpolar, a linear with two identicals. And then if you have a trig planar or a tetrahedron, I'm going to write you guys like a rule here, which I'm sure you already have. As long as the atoms around the central atom are the same, so then it will be nonpolar. So hydrogen, hydrogen, hydrogen in this trig planar. These fluorines are all the same in this tetrahedron. If they're not the same around the central atom, are different, then it will be polar. The other ones, so like here is an example of a tetrahedron that's polar. On paper, it can look kind of like the dipoles would cancel, but you got to remember it's really a three-dimensional shape. Linear, those are trickier. Those I just think about whether they'll cancel or not. So if it's a 2-atom and it's not the same element, then it's automatically going to be polar. And then if it's a 3-atom linear, the 2 atoms on the outside have to be the same. So it kind of follows this rule. To be nonpolar, it has to be able to cancel. So, for example, carbon dioxide is a linear nonpolar. But this HCN is going to be polar because if it were 2 nitrogens or 2 hydrogens, then they would have canceled, but they're not going to cancel. So I want you guys to take out your notes, or if you printed this sheet from when we did molecular shape, and now we're going to fill out this column. So tetrahedrons are nonpolar as long as the atoms around the central atom are the same. Trig pyramidals are always polar. Bents are always polar. Remember, that was because of the lone pairs. And then linears, they're nonpolar if the elements are the same. If it's a 2-atom linear. And we'll talk about 3-atom linears in just a little bit. So then also, when you get over here, remember the trig planar, they're nonpolar as long as the atoms around the central atom are the same. The trig planar bent still has a lone pair on the central atom, so they're always polar. And then the linear is that same rule if it's nonpolar if it's 2 identical atoms. Otherwise, it will be polar. So like here, oxygen, they're both going to pull equally, so it'll be nonpolar. And then lastly, the sp hybridization. These are 3-atom linears, and they are nonpolar only if the atoms around the central atom are the same. Otherwise, they're polar. So in this example here, the beryllium, that would be polar. It would have been nonpolar if they were both hydrogens on the outside or both chlorines. And this CNH is polar. Again, it would be nonpolar if they were both H's or both N's on the outside.